All right. Let's jump into it. I lied. There's not going to be any doing problems. There's more building so we can see what the heck we're going to do. Oh boy, you just love them videos where it's like, oh, let's get deep into math. But it is what it is. Let's go. But this isn't so bad, actually. Y'all have done stuff like this before. I promise you, you've done stuff like this before. You have. It's called, remember the slope of the tangent line? So let's talk about it. We got some we got some function, f of x. I don't know what f of x is, just some general thing. We'll start actually doing real functions soon. And what we want to do is we want to find a good approximation somewhere near a. Somewhere near a. So we're just going to look at a. Do you remember how we could do this? So let's just talk about what if there's, sorry, my graph doesn't line up perfectly with how it is. Do you remember slopes of tangent lines? Do you remember slopes of tangent lines? How would we get those? Sorry, let's make my dot bigger so it kind of doesn't go flat. That wasn't my thing. And then we'd be like, well, wait a second. Wouldn't you just take your derivative and go, well, the slope of the tangent line is equal to f prime of a, right? We get that. F prime of a would be the slope of the tangent line. We did that. That was the whole point of Calc 1. How do you approximate the slope of a curve? There's no such thing as a slope of a curve, but there's a slope of the tangent line, which can approximate the instantaneous rate of change of a curve. But there's that. And then we would set it up, right? Do you remember this? Did you do this? Y minus y1 is equal to the slope times x minus x1. If you took Calc 1 with me, I would keep asking you, like, stop putting the frickin' equations of tangent lines in y equals mx plus b. Leave it here. This is so much better. This is so much better. Because we're going to use it again. This is what we're going to use. So there's a fanciness to this. Like, did you know that this is actually written, this is f of x minus f of a is equal to the slope of the tangent line? Oops. Oh, I'm so sorry. Did I write in slope of the tangent line? I meant f prime of a times x minus a. Remember that? That's the fancy. These two things, that's the same thing. We're just, instead of using y's and x's and m's, we're using f's. We're just using f's. So, okay. You're like, oh, all right. Neat. Well, if you don't mind, I'm just going to add over. I just want to add over this f of a. And we'll put it out front too. So we're going to say, all right, so this f of x can be approximated by saying our f of a, would have just added over, plus f prime of a times x minus a. Just to give you a little idea, I don't know if maybe you remember from before, this is just a number. That's just a number as well. And then we have x minus a to the first. Oh my goodness, that looks like that looks like a power series. That looks like a gosh darn power series. It is. And then we change this f of x and we're like, nah, let's just call that thing y. And then I want to change the color because I'm not doing a good job of color coding and going, oh, here's your line. There's y equals f of a plus f prime of a times x minus a. You've been doing this. You've done this before. So what we can say here is a first degree polynomial. That's a line. You could call this one, instead of calling it y, you can call it p sub 1 of some polynomial. You're like, okay, why are we doing this? There's a reason. We'll finally get to it. I just can't get to it right at the beginning. So I'm pretty gosh darn certain this slope and this slope at x equals a are the same. F prime of a is equal to this, I wrote it as p sub 1 prime of a. They have the same slope. Hence they have, the slope of the tangent line. That's why we did all that stuff. You know what I mean? You know what I mean? Okay. Cool. But you know what? We could actually get a better approximation. we could get a better approximation. Because if we're looking at something we want to approximate, here's kind of the game that we're doing. We want to kind of approximate, like, I don't know, what's a plus, like, 1? Would that be a very good approximation on this curve? For the heights? Well, no, the heights would be off a little bit, right? They wouldn't be very close. So this isn't a great approximation. Let's do this. I'll just lose everything. Not a very good approximation for something near A. I mean, at A, it's perfect. Shoot, we could have done that in Calc 1. We could just stop talking about this now. Take a derivative. You know? Take a derivative. Plug in your value of A. There's your slope of the tangent line. Plug it in, make the points match. But we're not trying to do that. We're trying to get everything near it. We're trying to approximate a curve by using a power series. So here is what we did next when we were saying on our power series. So I'm going to call it P sub 2, but I'm just going to follow this form. Instead of writing it as f of A, I'll write it as C sub 0. Instead of f prime of A, I'm going to write it as C sub 1. Actually, no, I won't. No, I won't. I'm just going to write the next term that way. Oh, I'm so sorry. So we're going to write it in. We'll leave it as f of A. And then we'll write f prime of A times x minus A. But remembering here that this was C sub 0 and this is C sub 1. Well, if you remember from the power series from before, the next thing would be your next constant. It's just some constant times x minus A, and then it would be squared. This is now a quadratic. Or possibly we could call that thing a frickin' parabola. So now when we're going to approximate this thing, it's going to look like this-ish. Well, dude, if you start to zoom in, now that point's down here. Now that point's getting closer and closer and closer whenever we're near that A. Look at the green line. The green line approximates the blue line a little bit better than that purple line did it not? And here's our beginning. All right. Hang on. We're going to get to the result in just a second. Now I want to talk about the slope or the derivative. The derivative of our P sub. So what occurs here is we want to make sure that this polynomial, when we're trying to approximate that blue curve f, which I know is disappearing because I write way too much on there, we want to ensure that, you know, it's a good approximation near that point A. So we have to make sure that that P sub 2 and that f, the original, the green and the blue, must agree with f, and it's got to have the same value. Well, it does. Down here, it's got the same value. At A. It's got to have the same slope. Yeah, they got the same slope. They're matching. That's how we set it up. And concavity. Well, now it's got the same concavity. That line didn't have any concavity. So we have to have it follow these three conditions. And you don't have to do a lot of this. I do this part. And then you have to do the next part. So we're saying that if we plug in A into here, for all these values, we plug in A everywhere, it must equal the same thing as our f of A. But again, there's the point. We've set it up in such a way. We had to make sure that when you take a derivative at A, it's got to be the same thing as taking a derivative at f of A. That's the slope. No shit. No shit. So this is the point must match, the slope must match, and the concavity must match. So P double prime of 2 sub A is equal to F double prime of A. Oh man. Oh man. So let's take a derivative on P sub 2. Let's just take a derivative right on this guy right here. So we're just going to jump it aside, zoom in so we can see it, and go, all right, what's P prime, or P sub 2 prime of X? Well, we're going to lose our first term. That's just a constant. This is a constant times X minus A. This is another constant times X minus A squared. So we're going to lose that first term. And the next one, what's the derivative of a constant times x? It's just a constant. So that constant is f prime of a. Now we take a derivative on this part here. So the 2 will fall, and we're going to end up with 2 C2s times x minus a. So there is our derivative for P2. And lastly, we want to match up this concavity. Now here's the weird, and you don't really have to have a great understanding on this part, but we're going to do our best. So I'm going to take another derivative on this and go, all right, P double prime 2. Well, we're going to lose that constant. It's just going to go away. And the only thing we're going to be left with is just the constants, the 2C2 times x minus a. You take the derivative on something with an x and it just goes away. And we get, P double prime of 2 at some x. I'm writing it at x. I should have been writing it at a. That's my bad. Why am I writing this at x? Oh yeah, it's called muscle memory. Come on, dum-dum, you can do this. It's the concavity at that point. Are you hanging on? I know, we're about 11 minutes into this one. I'll try and keep them shorter. By doing this, we wanted to figure out, we're like, well, what the hell is going on here? I want to find C sub 2. That's kind of the point we're doing here, so we can plug it in and maybe we can catch a pattern. So if we actually, P sub 2, second derivative on P sub 2 of A, if you divide it by 2, it's equal to C sub 2. But we've already said that we needed to have the same concavity. Therefore, we're actually going to call this F double prime of A divided by 2 is equal to our C sub 2. And don't worry, there's going to be a pattern that's going to emerge. So then we can look and say that, well, this polynomial, what we had written in green, it's actually going to be written as such. It's our F of A from before, plus our F prime of A, times an x minus A, plus, and then we found out that our C sub 2, zoom in, Z sub 2, right here, we just solved for it and found out it's F double prime of A divided by 2, times x minus A, all squared, and then it will continue on. And then we're going to find that there is a very general way of writing all of these. This can continue on. This can continue on. And it's not as simple as, because there's a 1 underneath this one. And it's not 1, 2, 3. Unfortunately. Unfortunately. But that's going to be how, I don't need the plus because I'm only writing it as a second degree. Come on. Sorry, I'm a little rusty with this stuff, so please be patient. This P sub 2, that's that parabola we just used. What's in green? To approximate what's in blue. So by using this green polynomial we've just created, we can find points near A, and there'll be a great approximation. And again, you're like, why would I ever want to do this? Maybe you wouldn't. But there are times when things are not integrable. And this is going to be the way that we're going to get around it, and you'll get to see it later. So hopefully I've done something like this in class and said, hey, let's integrate this. Oh, wait, you go integrate that for me, please. And if you can, the money we will make together. But we can use these things to approximate it very, very well. So, all right, I will see you in the next. Hopefully some of that made some sense. We'll actually do a problem so you can see what we're doing in the next one. See ya.